Thanks everyone for being here. So this is going to be, I guess, the reverse talk, technology first, businesswoman, probably never, but still interesting. So I'm very happy to be here and tell you about some of the work that we are doing in the database group at the University of Washington. So of course, being database people living in the world of big data, we're looking at this problem quite extensively, and especially from three different perspectives. One is we're looking at how do we make big data management faster, and how do we make it more cost-effective as a cloud service. And this is very interesting, and I invite you to visit one of our recent projects where we have built our own big data management system that has certain really fun features, but I'm not going to talk about that. We're also looking at how to support data markets. People are buying, selling data. Data comes with license agreements. What do we need to support that? But I'm also not going to talk about this. So what I'm actually going to talk about is database usability. And this is just big thanks to Nadira and Youngchul, who are the main students working on this project, and also my colleague Dan Surju. So you might think, why is a database person talking about usability? Well, we heard this morning that databases are fun until we actually try to use them. And until recently, the people who were using databases were mostly database administrators, developers, and they actually enjoyed the fun. But now that we have a lot of people in companies, in sciences, who are not database experts, but need to analyze data, need to manage their data, we really need to focus on making sure that our tools can be used by this community. So there are many challenges related to database and using databases. So starting from just installing it, to loading the data, to then actually writing SQL queries on top of the data. The top part is a big problem, but at least we view this as a one-time problem. And typically, as we have seen in the talks earlier, there is someone on the team who will be skilled and willing to set everything up, perhaps as a cloud service, load the data, and make it available to the rest of the company. But the big problem is now we have a lot of users who are going to want to ask SQL queries, analyze this data, and who don't necessarily are database experts, but there's so many of them, we cannot help each one of them write these queries. They need to be self-sufficient. So how can we do this? And the observation is that it's very rare for people to do big data management, big data analytics by themselves. Typically, there's some sort of large, log, large collection of data, science, like a community-wide survey, and many, many users are accessing this data. So the key idea is, can we leverage the expertise that is growing among these users and automatically capture that expertise to then help the new coming users solve their problems? So that's kind of the key approach. So we are looking at many problems around this high-level topic. The two that I want to give you a brief overview today is, how do we help people just write SQL queries? And then given that they have written, let's say, Pig Latin script, and they're running it in their Hadoop cluster, but the performance is all bizarre, how do we help them debug what is going on? So to address the first problem, we wanted to say, OK, let's say I have a skilled user, someone who's smart, educated, but they're not necessarily database experts. They want to analyze a data set. They want to write SQL queries. How do we help them achieve this goal? And for this, we have built a system called SnipSuggest. And the system is best illustrated with an example. So being at the university, a lot of our customers are science users. In particular, we have a good collaboration with astronomers, and astronomers are collecting these large sky surveys where they have a lot of data, large collections of catalog information, images, and they allow all astronomers to just query the data. So here we have one astronomer, and he's interested in finding a star that has a certain brightness and is actually located near another star of interest. So John knows that he has to write some sort of select from where query, right? So likely select the properties that he's interested in seeing from the table that has the list of objects. But then he has to express the predicate on brightness, the predicate on location, and then he might pause and think, how should I express this? So how can we help him? If we look at the Sloan Digital Sky Survey, which is an important sky survey in the astronomy community, it has some 88 tables, 51 views, 204 user-defined functions, more than 3,000 columns. It's very tedious to go through the whole documentation. So we can do different things. So Joe could look at examples that are provided. And this is good, great starting point. But what if there are no examples that actually answer the question that he's interested in asking? He could do a keyword search over the log of past queries, but there's more than 100 million of them. And many of them, I can guarantee you, are not well-formed or just, different kinds of experiments that people have run. So this is also quite tedious. So instead, this is what our tool is going to do. We will allow, we're going to let Joe start to write his query. So he says select star, all the queries start like that, select everything from this table that we know is the most important table that contains all the object information. But now what? Well, now we can actually recommend. And if you look at the top 3 recommendations that our tool produces in this scenario, the third one has something called function get nearby objects. That sounds pretty much what we want, because we want the objects near a certain location, so we can fill in the location. Once we do this, well, now we have 2 relations, so we can automatically fill in the joint predicate. And then we pause, because we actually want the predicate on brightness. But what's interesting is all of us typically think we're doing something quite unusual and unique. More often than not, we're not. So a lot of people have used the predicate, and this is actually the 5th recommendation that our tool produces. The first 4 are more specific predicates on location. So we can fill in, again, the blanks for the constants, and we are done. So now the interesting question is, how do we make this magic happen? So the idea is we're going to look at, like I said, the expertise that accumulates over time. So we are going to look at this log of all the queries that people have written over a database. Here's a toy example with just customers and businesses. Imagine that we have a log with 30 times a query of the form, select everything from customers that actually happen to live in a certain state, and so on. We take this log, and each query in the log, we are going to represent as a feature vector, where each feature is a little bit a snippet of SQL. For example, the first query uses the customer table in the from clause. Well, that's a feature. It also has a predicate on state. Well, that's another feature. And we're going to kind of transform this log into these basically feature vectors. What we can do next is kind of organize all these queries into a workload DAG. We never want to actually build this DAG, but we want to just conceptually think of the queries as such. So the root of this graph is going to be the empty query, where there's nothing. And then we're going to see what happens. Each node in this graph is going to be some valid combination of features, such as node B will be just select from a table called B. And then we can connect all these nodes by saying, if I start from the root, which is my empty query, and I add one snippet at a time, I will go through a sequence of valid queries, all the way to these blue nodes, which are the actual queries that we have in the log. So what we can do now is we can look at kind of the conditional probabilities of these different snippets. Let's say if I'm at node B, and I look at my log, I will see that there are 30 queries in the log that have table B in their from predicate, in their from clause. Out of these 30 queries, 1/3 of them also have this predicate on ID. And we can kind of label all the edges with these probabilities. So now as the user starts to compose a query, they basically land somewhere in this graph. So perhaps we have a user that just said select from C, from customers from C. So they are here in this DAG. We can basically look at, we don't know what they want to write. We assume they want to write something similar to what other people have already written. So we will say, well, given where you are, if I look at other similar queries that are below you in the DAG, those are maybe the 2 most popular snippets that these queries use. Perhaps you want to leverage those. So that's the kind of overview of the approach. Does this work well? We have a bunch of experiments in the paper. But the bottom line is that what we tried to do is we took actually the Sloan Sky Survey query log, and we took queries and we stripped them. We removed a lot of components of these queries, and we saw how good was the tool at recommending back what was actually originally written in these queries. And we had significantly better results compared to other techniques, including showing only what is syntactically valid or showing only popular snippets without taking the context into account. So that's our system for helping people author SQL queries. So this is great, but now let me imagine that I write this SQL query, and let's actually change context a little bit. Let's say I wrote a pig-Latin script, which is a lot like a SQL query. And I run this pig-Latin script in a Hadoop cluster, and I get some sort of, odd results. So as one concrete example, imagine that I have written my pig-Latin script, debugged it on my tiny sample on my desktop. Now I'm running it on my 1 terabyte data set. It takes half an hour, but the result is wrong. It's not what I expected. I might think, well, OK, let me get a smaller sample, like a 10 gigabyte sample, rerun my query, but it still takes half an hour. And then I'm going to wonder, how come my debug run, which was so much smaller, took the same amount of time to process as my full run? Today, it's actually very hard to answer these questions. And that's one problem that even us in the database group we're running into. Sometimes the performance is strange, and it's hard to figure out what is going on. So can we build a system that helps answer these kinds of performance questions? So that's what we did with a system called PerfXplain, where as input, we're going to give a log of MapReduce jobs that executed in a cluster. More specifically, we actually used pig-Latin scripts. So we just observe this Hadoop cluster and collect statistics about everything that executes. And then we're going to take as input a query from the user about the performance of their tool, and we're going to produce explanations about what happened in terms of this performance. One important decision we made when we build the system is to answer performance questions that are relative. So we're not going to allow the user to tell me, why was this slow? Was slow for you? I think it was fast. Why do you think it's slow? So we said slow as compared to what? So we are going to allow questions of the form, why was my debug run, this run, the same speed as this run? I expected it to go faster. Or why was this job so much faster than this other job? So we're going to look at the relative performances, because then we can really see the differences between the two jobs and why the performance could differ. So to do this, as I mentioned, we are going to observe this Hadoop cluster and collect statistics. We collect statistics about the job itself, so how many reduced tasks were in the job, how many map tasks, and so on. About the input data, what was the size of that input data. We are also going to collect statistics about the cluster. How busy was the cluster? What else was going on in the cluster? How was the cluster configured, such as the block size? We're going to collect these statistics for each job. But like I said, we want to look at performance differences between jobs. So in our log, we don't store just the jobs themselves. We think of them as pairs. We're going to look at different pairs of jobs and look at what was interesting between this pair. So of course, we're going to look at different features that the pair had. The basic features are going to have the actual values of the statistics collected for each job. But we found that if those were the only features that we were collecting, when we said, why was this job faster, the explanations would come back of the form, because this one used 36 reducers and this one used 34 reducers. And we said, do I really care that it was 36, or do I just care that one had more than the other? So we ended up building a hierarchy of features, where at the top, we just say for each feature, we just indicate whether the two jobs had the same value or a different value. So if I don't care about anything more than the fact that it was different, that's what our explanations should say. At the bottom level, we have the actual values, if the values themselves are important. And in the middle, we just say, was this greater than, or similar, or much less than? Or in the case of categorical features, what was the change? Maybe this was running a filter, this was running a join. So we have this hierarchy of features that allows us to produce kind of general explanations when we don't care about the details, but get into the details when necessary. So once we have this, this log, we will allow the user to write these performance questions in a SQL-like language that really has 3 clauses. So we say, given these 2 jobs, so here we identify the 2 jobs, J1 and J2, that we are interested in. So J1 is perhaps my full run, J2 is my debug run. I will say I expected these jobs to have a certain behavior. I expected J2 to be much faster than J1. That's what I expected. But I observed that J2 was actually taking the same amount of time as J1. Why is this? So that's the kind of question we will ask. We can also say, use kind of an extra despite clause that helps us clarify our question, the context of our questions. So in this case, I can say, in spite of the fact that J2 processed less data, I observed that it took the same amount of time, and I expected it to go much faster. And we will see that the despite clause allows us to generate much more relevant explanations. So here's the concrete example using the actual feature hierarchy that we have. So I have my two jobs, J1, J2. J1 is the full, J1 is the debug run. I will say that I expected the duration to be greater than, so J1 to be much faster than J2. I observed that they were similar, and all of this despite the fact that the input data size was much smaller for J2. So given this as an input, what Pixel will do is now generate an explanation. The explanation is, again, going to be a predicate on these features of the pair of jobs. So here's our query. In this case, actually, any guesses as to what was the explanation? This was actually a real example. So I'm sure some of you ran into this. So we have one job that processes a lot of data, another job that processes much less data. The two took the same amount of time on the same size cluster. The problem was the block size. The block size was large, so the runtime was actually the time to process one block. It didn't matter how many we had because they were all processed in parallel in both cases. And that's the explanation that actually our tool generated. And this is despite the fact that this is just kind of the despite clause that comes back because our tool can also extend the despite clause. So why do we actually need this clause? So initially we asked the question. We said, I have these two jobs. I expected J2 to be much faster, but instead they took the same amount of time. What our tool said is because they use the same number of instances. Because in general, when two jobs use the same number of instances, they tended to run in the same amount of time. But in this case, this explanation doesn't help us at all. But when we say, no, J2 actually processed less data. So only look at those jobs where J1 processes more data and J2 processes less data. So then I expect J2 to be faster. Why isn't it? And when we add that despite clause, then we have kind of a much more accurate explanation. And because this despite clause is so useful, our tool can actually grow it on behalf of the user to produce these kind of more relevant explanations. So how do we do it? So when we actually produce these explanations, we get the user input query as input, and we will try to generate first the despite clause, where we will say, if I have my all my examples, the red ones are the pairs that actually performed as the user observed. The blue ones are the ones that performed as expected. The despite clause tries to maximize the probability of seeing the expected behavior. So given what I have, can I find the smallest subset of data that covers my point of interest, my pair that I'm interested in, and captures all the reasons why this pair of jobs should have behaved the way I expected it to behave? Now that we find this, we're going to say, all right, given only this subset, in this case only the jobs where J1 processes more data than J2, let me find an explanation. For the explanation, we want it to be precise, so we want a predicate that maximizes now the probability of seeing the observed behavior to explain that behavior. But of course, so if I have a high probability, then I have a precise explanation. But I could generate explanations that say, because you executed on May 14th at 3:22 p.m., therefore you saw this behavior, which is a very precise explanation, but again, completely useless. So we need to counter the precision requirement with a generality requirement. So we say, well, because the explanation should actually try to cover a lot of cases. It needs to have kind of good support. It needs to be something that is likely to occur in many cases. So when we generate these explanations, we kind of maximize the weighted combination of this generality and precision. Does this work well? So this is just, we ran some experiments on EC2 where we actually executed pig-Latin queries and collected different values. And the experiments are again in the paper, but when we looked at the explanations that we were generating, they were achieving kind of a much better trade-off in terms of generality and precision compared to alternate techniques that we examined for generating these kinds of explanations. So the idea, again, is that we have these users. Users are smart, but they need extra tools to really be self-sufficient. And PerfXplain is one of those tools trying to help explain the performance of queries in these large clusters. So what I would like to do is spend the last few minutes just telling you a little bit more about our ongoing work. So as I said, we are a database group. We are looking at different aspects of big data management. One of those is usability. I talked about helping users write SQL queries. I talked about helping users debug the performance, but there are many, many other challenges. The one that I'm very excited about that we are tackling right now is to say, well, users are all moving to the cloud. If I want to analyze my data in the cloud, I go to Amazon. They say, sure, use any of our tools. I pick, say, Amazon Elastic MapReduce, and they say, how many instances do you want? My answer, I don't know. And then we actually tried, we asked users, like, say you have 100 gigabytes, how many instances you would pick? Any one of us here would say, pick 20, right? But people say 100 gigabytes, disks today are terabytes, one should be way plenty. Right, so we just don't have, even experts probably don't have a good sense. So we're looking at another method where we tell the user, okay, just show us your data. When the user shows us their data, we can analyze that data and we say, aha, so if you're willing to pay that much money, fixed cost per hour, those are the kinds of queries we can run, and that's the performance guarantee we offer. You're willing to pay more, well, these are the kinds of queries we can run, or we can run them much faster. Or you're willing to pay less, well, this is what we can do for you. So we look at the data, and we tell the users what their options are. We're also looking at other challenges in terms of usability. One I mentioned is around buying and selling data. If I buy a data set today, all the data sets come with really long license agreements, and it's my responsibility to make sure I don't violate it. But I don't even want to read it. So what we have done is actually have built a system where you just load the license agreement into the system. Of course, we don't do the parsing of the English text, so it has to be nice SQL-like expression of the license, which is, but we'll let the lawyers worry about that. But once it's in the database, we can automatically, very efficiently, actually enforce these licenses and tell users if they are about to violate them or not. And finally, we're also kind of playing the game of visual data analytics, where we let users just forget SQL queries, use Tableau, drag and drop, click on things, but then how do we help them within that cycle clean their data, integrate their data, and kind of look at their data in a more holistic fashion. So lots and lots of really interesting projects. So the conclusion is simply data management, very important today. That's why we're all here. Building fast tools, extremely important. We are in the business of doing that. But thinking about the usability, even though we're not HCI people, thinking just about useful tools that make life easier for people is also kind of a lot of fun and very important. So that's all I want to say. Thank you very much.
So we have a couple of minutes for questions.
Can you maybe say a little bit more about how you cost the queries when you give your recommendations on configuration?
Oh, how do we cost the queries? So the basic strategy is we use kind of machine learning. So we build a model. We look at all the features of the queries, which is a state-of-the-art approach. Look at different features of the queries, build a model of how long the queries will take, and we build that model for different configurations. So then we have kind of the estimated runtimes based on the features, and we do that for, so kind of we look at the data that the user gives us. Given the data, we generate kind of representative queries. We look at the plans for these queries, get features and runtimes of these plans, cluster them, and then we kind of have clumps of queries and say, this is one tier, one group of queries that you can run for that time at that price. Here's another group, different time, different price. It's pretty cool. And actually, so far, it works, but the paper has not been written. So maybe next year I can talk about it.
There's one question there.
I'm curious for the PerfXplain if you're looking at extending that to maybe start adding like net stat statistics, and so that you get sort of a systems holistic approach instead of just a more smaller microcosm of what the problem might be.
I think that's a great suggestion, and our tool is pretty flexible because PerfXplain simply views the log of jobs as a set of features. So we can plug in pretty much any features. The main thing to think about is, of course, will the user be able to understand what the features mean, which is why we find often a hierarchical description of the features, hiding details as much as possible, works well, so the explanations are not too detailed. But the system is extensible with all kinds of features.
All right, so I think we are running out of time, so maybe during the coffee break. So thank you very much, Magda.
Thanks.